Okay, let's unpack this. Welcome back to the Deep Dive, your shortcut to being brilliantly well-informed.
Great to be here.
Today, we're diving headfirst into, well, some pretty mind-bending research. It honestly sounds like science fiction, but nope, it's real.
Very real.
And it could seriously redefine how we think about quantum computing. You've sent us this incredible new work from the University of Osaka, published in NPJ Quantum Materials. And our mission today is, to cut through the complex physics and get you straight to the aha moments. We're talking heavy fermions,
Yeah.
quantum entanglement, and something called the Planckian time limit. It seems like these all connect to offer a really new path for next-gen quantum computers.
That's exactly it. And what's truly fascinating here, I think, beyond just how new it is how this research takes these really deep quantum ideas.
Right, like entanglement.
Exactly, entanglement, and even the smallest possible unit of time, Planckian time. And it shows them not just as theory, but as something, observable, measurable.
In an actual material.
Right there in a unique, solid-state material. That's the key. It's an experimental observation. A team in Japan working together found these things called heavy fermions.
Okay, we definitely need to get into what those are.
We will. But they're essentially electrons acting like they're much, much heavier. And they saw them exhibiting quantum entanglement.
Wow.
And here's the real kicker, like you mentioned. This entanglement seems to be controlled by Planckian time.
The universe's shortest time unit.
Basically, yeah. The fundamental quantum limit. This isn't just an interesting quirk for physicists. It really underscores how robust quantum mechanics can be. And importantly, it opens up genuinely new directions for quantum tech.
Okay, so let's start with those heavy fermions. It just sounds like a contradiction, doesn't it? Electrons are tiny. How can they be heavy? And why are they the ones involved in quantum entanglement here?
Yeah, it's a great question. And the name is a bit misleading if you think about literal weight. It's not that. We're talking about electrons with a greatly increased effective mass.
Effective mass.
Okay. So imagine an electron trying to move through a material. Normally, it zips around pretty easily.
Right.
But in certain materials, these moving electrons, the conduction electrons, interact really, really strongly with other electrons that are kind of fixed in place. These localized magnetic electrons.
Ah, okay, so they're bumping into things, metaphorically speaking.
Sort of, but it's more like they're dragging something incredibly heavy with them because of these constant quantum interactions. It's like the electron gets dressed by its interactions.
Dressed?
Yeah, it accumulates this cloud of interactions around it, making it behave as if it's hundreds, maybe thousands of times more massive than a free electron. That's a heavy fermion.
Okay, so it acts heavy because it's so tangled up with its environment.
Precisely. And this isn't just some weird side effect. This behavior leads to really unusual properties, like unconventional superconductivity. That's why these materials are a huge deal in condensed matter physics. And connecting it back to entanglement, these intense interactions, this heavy nature, they create the perfect storm, the conditions for what's called a quantum critical state.
Quantum critical state.
Yeah, it's a state where quantum fluctuations are absolutely rampant. And it's within that specific state that these heavy fermions were found to be quantum entangled. They are the players showing this behavior.
So the heaviness and the interactions are actually why they can get entangled in this observable way.
That seems to be the crucial link, yes. It sets the stage perfectly.
Okay, that clarifies the heavy part. But now this is where my mind really starts to bend. The research says this entanglement is controlled by Planckian time. Planckian time. That's like 10 to the minus 43 seconds, the absolute fastest anything can happen, theoretically.
That's the one. It's the fundamental unit of time in quantum mechanics, the shortest duration that really has physical meaning in our current understanding. Below that, space and time get fuzzy, and quantum gravity effects would likely take over.
So how can something so incredibly small and fundamental be controlling entanglement in a chunk of metal? What does controlling even mean here, and why is that so important?
Right, that's the core of it. When they say controlled by Planckian time, it means the lifetime of the entangled state, how long it persists, and maybe even the rate at which it fluctuates or decoheres, seems to be dictated by, or at least approaching, this ultimate quantum speed limit. Yeah. It's like the universe's own tiny fundamental clock is ticking for this entanglement.
Wow. Okay.
And this isn't just happening randomly. It's specifically in that quantum critical state we mentioned, where everything is already buzzing with quantum activity.
So it's linked to that critical state.
Exactly. Dr. Shinichi Kimura from Osaka University, one of the researchers, put it nicely. He said, "Our findings demonstrate that heavy fermions in this quantum critical state are indeed entangled, and this entanglement is controlled by the Planckian time." He calls it a direct observation, a big step in understanding how these things connect.
The direct observation. That's
Yeah,
huge.
it is. And it leads to that deeper question you raised. Why is seeing entanglement tied to the Planckian limit so profound for quantum computing?
Yeah.
Well, it suggests this form of entanglement is incredibly fast, fundamentally limited only by the universe itself, and potentially very robust because it's tied to these basic constants. That's exactly what you want for quantum computation: fast, stable entanglement.
Like finding an engine that naturally runs at its absolute theoretical max speed and it's durable.
That's a great analogy.
Yes.
It's finding that potential built right into the material's physics.
Okay, this is making more sense. It's not just theory. They saw this. You mentioned the material, Cerium-Rhodium-Tin, CeRhSn. What's special about that compound, and what did the experiments actually show? How did they see entanglement?
Good question. The material choice is key.
Yeah.
CeRHSn is part of this family of heavy fermion systems. What makes it particularly interesting is its atomic arrangement, a quasi-Kagome lattice structure.
Quasi-Kagome sounds complex.
It is a bit. Picture atoms arranged in a pattern, sort of like interwoven triangles, like you might see in some Japanese basket weaving, hence the name Kagome.
Okay, I can visualize that. Lots of triangles.
Right. And in physics, that kind of geometry often leads to something called geometrical frustration.
Frustration, like the atoms are unhappy.
Huh, in a way. Imagine putting tiny magnets at the corners of a triangle, and each one wants to point opposite to its neighbors. You can't satisfy all three at once. One is always frustrated.
Ah, I see. There's no stable up-down-up arrangement that works for all pairs.
Exactly. That geometric frustration in CRHS prevents the electron spins from settling down easily into a simple magnetic order. It keeps things dynamic and complex at the quantum level. That frustration is actually a feature, not a bug, for creating interesting quantum states.
So the structure itself promotes this weird quantum behavior.
It seems to contribute significantly, yes. It encourages these strong correlations and fluctuations. So the researchers took this material and did really careful measurements of its reflectance spectra.
Reflectance spectra, shining light on it.
Essentially, yes. Shining light of different frequencies, from infrared up to higher energies, and measuring precisely how much light reflects back. By analyzing the patterns in that reflected light, the spectra, you can deduce a huge amount about how the electrons inside are behaving, what energies they absorb, how quickly they scatter.
Like listening to its quantum music.
That's a nice way to put it. And CeRhSn was already known to be weird. It shows non-Fermi liquid behavior at relatively high temperatures.
Meaning it doesn't follow the usual rules for electrons in metals.
Right. Most metals behave like a predictable Fermi liquid. But the electrons in CRHS, because of those strong interactions we talked about, act more chaotically, more like a turbulent quantum fluid. And remarkably, this weirdness persists almost up to room temperature. Usually you need extreme cold for these effects.
That's unusual in itself.
Very. But the crucial part was in the analysis of those spectral patterns. They found that the data across different temperatures and frequencies could be described by a single mathematical scaling function.
A single function for all that complex behavior.
Yes, and that specific mathematical form is considered strong evidence, a kind of fingerprint for quantum entanglement among the heavy electrons. They also saw directly from the data that the lifetimes of these heavy electrons were approaching that Planckian limit.
So the light reflection pattern literally revealed the entanglement and its timescale.
Exactly. The consistency of the data with this scaling theory provided the direct experimental proof. It wasn't just a hypothesis anymore. They included detailed images and graphs A, B, C, in their paper showing this scaling very clearly. It's meticulous work.
Wow. Okay, that paints a much clearer picture of the evidence. Which brings us finally to the big so what. For everyone listening, you've walked us through heavy fermions, Planckian time, this specific material. What does it all mean for the future of quantum computing? Why is this observation a potential game changer?
Right, to pay off. Well, as we keep saying, quantum entanglement is the absolute bedrock, the key resource for quantum computation.
No entanglement, no quantum computer.
Pretty much. So the ability to find, confirm, and understand entanglement happening robustly inside a stable, solid-state material like CeRhSn, that offers a potentially much more practical path towards building quantum computers.
More practical than what we have now.
Well, think about many current approaches. They often rely on trapping individual atoms with lasers or using superconducting circuits cooled down to near absolute zero. These systems are incredibly delicate, prone to errors, and really, really hard to scale up.
Right, you hear about quantum computers needing these extreme conditions.
Exactly. It's a massive engineering challenge. But imagine if you could have a material where useful quantum entanglement is just an inherent property, something that happens naturally, maybe even closer to room temperature because of the material's own physics.
Like finding the right kind of crystal or alloy.
Potentially, yes.
Yeah.
It shifts the challenge from building everything delicately from scratch to perhaps finding and engineering the right materials that already do some of the quantum heavy lifting for us.
That sounds a lot more scalable, almost like conventional electronics manufacturing eventually became.
That's the long-term hope, though we're obviously very far from that. But finding materials like CRHSN points in that direction. And that Planckian time observation isn't just academic.
Oh, so.
It gives designers a fundamental timescale to work with. Knowing the speed limit, the coherence time dictated by this fundamental constant, helps understand the potential and limitations for processing quantum information in such systems. It's a crucial parameter for design.
So it informs how you'd actually build something with it.
Precisely. And digging deeper into these entangled states could really revolutionize how we process quantum information. It opens doors to potentially new types of qubits or quantum logic gates based on these collective electron behaviors. So it's a double win. We learn more about fundamental physics, these weird, strongly correlated electrons, and we get potential blueprints for future tech.
So it's about translating this deep quantum weirdness into something usable in a solid, potentially manufacturable material.
That's the core of it, moving from fragile, isolated quantum states to robust, intrinsic properties of a material. That's a huge leap conceptually towards practical quantum computing.
It really does feel like a significant step. Okay, so let's recap this deep dive. We've heard how scientists in Japan studied a material called CRHSN and found that its heavy electrons acting heavy due to strong interactions exhibit quantum entanglement. And incredibly, this entanglement seems to operate on a timescale linked to Planckian time, the universe's fundamental clock tick.
That's the essence of it.
This could mean a new, more robust, solid-state path towards quantum computers, maybe moving beyond those super delicate systems we often hear about. So hopefully you listening now have the key insights into how these heavy electrons might just reshape the future of computing. Truly mind-bending stuff, but with real potential down the line.
Absolutely. And maybe this leaves you with a question to think about. If we can really harness this kind of robust, intrinsic entanglement in solid materials, if CRHSN is just the first example, what kinds of problems that seem completely impossible today might suddenly become solvable?
Like what?
Well, think about designing perfect catalysts for green energy, simulating protein folding accurately for new medicines, optimizing incredibly complex global systems, problems where the sheer number of possibilities overwhelms current computers. Could these material-based quantum systems finally crack them? It's definitely something to ponder as this field keeps racing forward. Keep watching this space.